So I'm going to talk about something that I've been doing for a while, but I think has a nice story to tell about how entropy, especially thermodynamic entropy, emerges in out of equilibrium situations. And this is something that I've been doing for, seems like forever, with my former student Felix Hall, who's in the audience, he's at UBC, and Logan Ayagam, who's at ICTS in Bangalore. And I'm sorry to throw out this laundry list of references, but hopefully the talk itself will be self-contained. And there's a series of related papers written by our friends at MIT and from Haifa and SF State, which I'll say something about as we go along. Okay, so I'll start with a summary. I'll tell you 3 statements, which I'm going to sort of explain in the rest of the talk. So first is that for systems in local but not global equilibrium, the entropy current, there is an entropy current, there's a local current for entropy, and its Legendre transform you can think of as a free energy current, and this free energy current is a Noether current. We know this statement to be true in the context of stationary black holes from the world construction, but it transcends that. Furthermore, local equilibrium is characterized by an emergent topological symmetry, which leads to an idea called thermal equivariance, which I will explain. But the basic idea is that the diffeomorphisms along the Euclidean time circle in thermal field theories ends up being a gauge symmetry in local equilibrium. The first 2 statements seem mutually contradictory because on the one hand, if entropy is a Noether current, and on the other hand, it's a current associated with a gauge symmetry, how the hell can entropy ever be produced? And the mechanism by which entropy ends up being produced in physical space is very similar to how Toft anomalies work in quantum field theories. So a statement that I'll try to prove to you at the end of the talk is that the net entropy is conserved, but it's a net entropy including the topological contributions. The physical entropy is produced by being sourced in the superspace directions, and in some sense, there's an inflow of entropy from superspace to physical space, which leads to entropy, the second law of thermodynamics. Okay? I think these statements ought to hold very generally. The only context where I know how to prove this is the context I'm going to describe to you is local equilibrium, which is hydrodynamics. Okay, so let's start by asking the following question. Why is entropy so hard? Okay? Why is thermodynamic entropy so hard? And why is entropy current so hard? Now, most systems have conserved charges, and conserved charges are something that you can get by looking at the UV properties of the theory. You look at the UV property and then you coarse grain the theory. These conserved charges make sense both in the UV and as you coarse grain down to the IR. Entropy, on the other hand, is an IR concept with no manifest UV occurrence. It's very clear, for example, if you think about it in area CFT, where entropy is the property of horizons, while conserved charges live in the asymptotic boundary. For example, if you look at the fluid gravity context, where you have black holes in near equilibrium dual to fluids on the boundary, the fluid stress tensor lives on the boundary of ADS, but the entropy current is the pullback of the horizon area form onto the boundary. So in some sense, you have to go into the IR of the geometry and bring back the entropy to ask what it means in the field theory. What I said here is the pullback of the horizon area. To be a bit more clear, I should have said that this is really the pullback of some kind of apparent horizon area because the event horizon area, for reasons that we just heard about, doesn't really make sense in general. The event horizon is a teleological concept, so it's not clear that assigning the entropy current to the event horizon area makes sense. In the previous discussion of the fluid gravity, the fact that you're sort of looking in the near equilibrium long wavelength regime blurs the distinction between event and apparent horizons. It's not true in more general contexts. For example, if you look at a flow where you take the global Schwarzschild black hole and you slice it in Poincare coordinates, what's called the conformal soliton flow, then the event horizon as seen by an observer who lives in the Poincare patch is this sort of flaring out blue surface that hits the boundary in finite time. So the event horizon area actually is divergent in finite time, whereas the apparent horizon area is always constant. So the fact that apparent horizon area should be taken seriously, as far as I know, was first mentioned in this nice paper by Schester and Yaffe when they were trying to do model heavy ion collisions by colliding shock waves, and it's a recurrent theme in recent discussions, for example, by this paper by Aaron and Netta from a few months ago. So given this sort of dichotomy between conserved charges living on the boundary and entropy current sort of living deep in the bulk, let's use this intuition to ask, how does entropy come by, and how do we prove the three statements I told you? So I'll start with the simplest context of equilibrium. So general thermal equilibrium can basically be obtained by studying dynamics of quantum fields on any stationary space-time with a time-like killing field. Okay? And so all that says is that you basically do statistical field theory on a Riemannian manifold where you have a Euclidean time circle fibered over some spatial base. So that's what we usually sort of don't think about it in such a sophisticated language. We think of homogeneous temperature, and all you think of is the Euclidean time circle, which is uniform over some space or over spatial geometry. An interesting statement which follows from this is that if you think of a hydrodynamical approximation to any interacting quantum field theory, then fluids always admit hydrostatic configurations where the velocity of the fluid is basically aligned with the thermal fiber, with the killing field of this Riemannian space. And another corollary that goes back a few years to these people is that it's very easy, at least in a long wavelength limit, when the spatial geometry and the thermal fibration are slowly enough varying on spatial scales, there's no temporal variations, it's equilibrium, they can be obtained from an equilibrium partition function. This equilibrium partition function is nothing but a generalized pressure function where you have allowed yourself the freedom to have spatial gradients, but no temporal gradients, because you're talking about equal time correlators. Okay? So in some sense, this gadget W is simply the generator of energy momentum correlators at equal times in equilibrium. Now, this generalized pressure function is a functional of this killing field, but I can rewrite that killing field in terms of fluid dynamical data. So I've sort of written this in terms of this killing field I've written in a language that's amenable to fluid dynamics. The killing field of the stationary spacetime is identified as the velocity of the fluid divided by the local temperature. It's simply the statement that when the inertial frame for the co-moving fluid is sort of aligned with this killing field, but the scale is set by what the local temperature is doing. It's just taking care of the redshift. So now that given this generating functional, I can vary this generating functional with respect to the spatial source, with respect to the metric, and get the energy momentum tensor, the conserved current. That's just a Noether construction. You can ask, what is the entropy current? Where does the entropy current come from? The same variational principle that gives you the energy momentum tensor, this energy momentum tensor is the variation of W with respect to g mu nu divided by root g with factors of 2, if you like. But that when you do that variational principle, you integrate usually by parts if you have derivatives. And those integration by parts leave behind a boundary term. The entropy current is nothing but this boundary term plus a canonical piece that comes from the action. This construction should be familiar to anyone who's seen the world construction for black hole entropy, because it's exactly the same thing, but in a context where there is no dynamical gravity. The world construction is a construction that happens in a stationary black hole spacetime with the equations of motion imposed. Here I don't need to impose any equations of motion because the hydrostatic configuration immediately solves the fluid equation, and the entropy current comes out on the nose as a Noether current. Okay? So that explains the statement at the level of equilibrium, but my statement was stronger because I said the statement more generally in local equilibrium, away from in local equilibrium, which doesn't mean whereas this is a statement about global equilibrium. Now here, I'm going to invoke a theorem that was proved a few years ago by Shantanu Bhattacharya, who basically undertook the following exercise. You can ask, under what conditions can you construct an entropy current? And she showed that it's always possible to construct a hydrodynamic entropy current which satisfies the second law, that is the entropy current has non-negative divergence locally, as long as leading order dissipative terms are of the right sign. So for example, the system has friction, not anti-friction, and hydrostatics is consistent with the statement I just said before about the equilibrium partition function. I won't sort of go through the theorem the way she proved it. I'll just tell you an answer which sort of follows from our analysis. So a better way to sort of invoke this theorem is to basically rewrite the second law of thermodynamics directly in terms of the free energy current. So now I define for you this free energy current, which I hadn't defined before. So there's a local mysterious object, the entropy current. I've instead now added to it a piece of the usual energy momentum tensor and converted this into a free energy current. And the second law statement can be rephrased as a statement that the divergence of this n minus the energy momentum tensor dotted with the lead derivative of the metric along this vector beta, which is no longer a killing field, has to be positive definite. So what you can do is you can try to take this as a functional equation, and you can try to solve for all possible solutions to this functional equation. And I'm going to solve this in two steps. I'm going to solve for the subspace where delta is non-zero and positive. And the second step, I'm going to solve the homogeneous equation where delta is 0. So this theorem can be rephrased as a statement that it's always possible to find the solution to the subspace where delta is non-zero by a dissipative energy momentum tensor that takes the following form. It's parameterized by a 4 tensor, which is symmetric in its first two and last two indices, and symmetric in the exchange of the two pairs. And delta is basically given by the contraction of the 4 tensor with two lead derivatives of the metric. I cheat a little bit because this 4 tensor is not really a tensor. It's a tensor value differential operator because I buried any order derivatives because I want to make a statement that's true to all orders in the gradient expansion. Okay? So think of this delta as a tensor value differential operator that that defines a positive definite inner product on the space of two tensors. Okay? The homogeneous equation, where delta is 0, turns out to have non-trivial structure, and the details are not important. It turns out that the classes of solutions include the hydrostatic case that I discussed before, but they include 7 other classes that do not lead to entropy production. So you might think of the space of all fluids as the space of fluids that respect equilibrium, so they're ideal fluid generalizations, they're dissipative stuff, and then there's lots of stuff that don't produce entropy but are not equilibrium. Okay? So just to give you an intuition for what this is, so the Hall conductivity that people see in quantum Hall systems is an example of a non-dissipative but non-equilibrium gadget. So I'm now going to sort of move on toward the second statement, which is the statement about thermal equivariance. But to do that, I'll tell you some empirical facts that was understood in the context of writing down these, understanding these adiabatic class of solutions. So first is that we want, since this class of solutions don't produce entropy, they're conservative. So you might ask, could you write down an effective action that captures this data? We empirically notice that the effective action works provided you work in an enlarged space of fields. You don't talk about one set of fluid degrees of freedom. You talk about 2 sets of fluid degrees of freedom. But the moment you enlarge your space of configurations to include 2 sets of degrees of freedom, you have far too much ambiguity. To reduce those ambiguities, we hypothesized a new symmetry principle that ensured that this equation with delta equals 0 was obtained as an identity. Okay? And in that context, it was still true that the Noether current was the free energy current was the Noether current. But now of the symmetry that we proposed, I'll explain the symmetry in a while. So all of this was empirical. I'm going to give you a reason why this must be true and where this comes from. But to do this, I'm going to sort of switch gears and for a brief while talk about how hydrodynamics emerges from a microscopic quantum field theory. So hydrodynamics, as I'll say a bit more precisely later, is a theory of response functions. Classical hydrodynamics is a theory of response functions. You sort of set up some system, which is, you drive it away from equilibrium by turning on external sources, and then you measure the response the system has after you've driven it away from equilibrium. And response functions are, in modern language, once out of time ordered correlators. They're not twice out of time ordered, as we've heard in the discussion of chaos, but they're computed by what more familiarly is called the Schwinger-Keldysh formalism, where I've taken Alex's picture and inverted it 90 degrees. So I start with some initial state, I evolve it forward, I then evolve it back and glue it at the future with a maximally entangled state, except that my maximally entangled state here is not normalized. And if I'm in a thermal system, after I evolve it back to the initial, I sort of evolve it back to the initial state and then take it back an amount by Euclidean evolution of beta to sort of ensure that I'm in a thermal state. So what I've written here is true for any density matrix, but I'm only going to talk about thermal density matrices. So the generating functional for correlation functions in this context is simply you take an initial density matrix, you evolve it forward with some sources, you evolve it back with some sources, and then take a trace, which is what this future turning point is doing. And this allows you to compute time-ordered correlators, and which includes, in particular, the class of response functions we are interested in. Now, there are two statements that sort of follow very naturally from the very nature of this Schwinger-Keldysh generating functional. And these are the two sum rules that I want to highlight. One is, if you had turned on the same sources for the left and right, you've basically done nothing because the unitaries cancel if you're doing unitary evolution. And if you look at how the source operator coupling goes, turning on the same J right and J left couples to a difference operator. It couples to O right minus O left. And that means that correlation functions of difference operators happens to vanish trivially, independent of dynamics in the Schwinger-Keldysh theory. Furthermore, if you're in a thermal state, you can take an operator that's here and move it back through Euclidean time and bring it down here, which leads to a second set of word identities, which says that if you insert an operator on the top part of the contour and insert the corresponding operator on the bottom part, but shifted by I beta, that correlation function also is 0. This is sort of the generalized KMS condition that one would have. Okay. Now, I'm going to use a shorthand for later that I'm going to define an operation delta beta, which basically is the difference of an operator at time t minus the operator time shifted by I beta. Okay? So it measures how much an operator has been taken around the thermal circle. So these two statements are true, and they're sort of true by construction in the Schwinger-Keldysh theory. And so this could be, for example, we could be talking about n equals 4 super Yang-Mills or QCD or what have you. And what we're after is we have these sort of UV degrees of freedom, and we want to start with those UV degrees of freedom and integrate out all the high energy modes and write down a theory for just the low energy modes. That's what hydrodynamics is. It's a long wavelength theory. So I want an effective action for the low energy modes, having integrated out the high energy modes, but not for the usual Euclidean field theory, but for this particular Schwinger-Keldysh contour. The trouble is, while the action for the Schwinger-Keldysh theory is factorized, because of my initial thermal density matrix, I have correlations across the contours. The left-right correlation functions are non-zero, And if I start integrating out high energy degrees of freedom, those left-right correlations will lead to a non-factorized low energy action. This is the same problem I mentioned a slide ago, that once I do doubling, I need some rules, otherwise unconstrained rules will not respect the unitarity of the Schwinger-Keldysh evolution. So we need statements like these word identities to hold even in the low energy theory after integrating out high energy modes. And it's not clear a priori how to do this. So we have a proposal which can be checked in various cases of encoding the data coming from these symmetries, from these sum rules, into a set of symmetry statements. And these symmetry statements should better be robust under integrating out high energy modes. In other words, they should be robust under coarse graining, otherwise they're reasonably useless. And the only kind of symmetry statements that are powerful to survive coarse graining are symmetry statements that involve some kind of topological structure. And indeed, it turns out that the right structure is to encode the Schwinger-Keldysh construction in the framework of a BRST superalgebra. What that does for us is that it will allow us to write down the correct right-left couplings and write down what in a language that was introduced by Feynman and Vernon are called influence functionals that are relevant in the low energy theory, but these influence functionals will respect the microscopic constraints of unitarity. I can say this slightly differently. You start from a microscopic theory and integrate out the high energy stuff to get the macroscopic low energy theory, and it has to have two sets of degrees of freedom. In the right-left language, it has to have an average, or what is usually in stat-mech literature called the classical fields, and these are the fields that dissipate. These are the fields that you actually measure. These are the fields you actually sort of see in your response functions. But you see, the very statement that there is dissipation is inconsistent without there being corresponding fluctuations. Because in any quantum system, there always are quantum fluctuations, but moreover, when you're talking about thermal systems, there are, in addition to those quantum fluctuations, stochastic thermal fluctuations, and both of these have to go hand in hand for the system to make sense. And there has to be some set of variables that encapsulate those fluctuations. So there must be, in addition to the average fields, there must be quantum stochastic fluctuation fields. So rather than sort of give you a sort of derivation or a motivation for where this comes from, I'll just say that all of these couplings can be, how these average, the average and the difference fields are coupled in terms of these influence functionals can be understood by invoking this BRST symmetry and enlarging our considerations to working in a superspace that's locally Minkowski space with two Grassmann coordinates appended and asking our questions there. So I'll just flash this algebra for you. This is the algebra that we derive from the considerations of thermal Schwinger-Keldysh construction. There are two sets of supercharges that come from basically the first sum rule, which says that difference operator correlators are 0, and then there's the statement of thermal equivariance, which I'll explain in a moment, which tells us how the KMS condition is implemented. Rather than sort of give you the sort of overall story, let me say that the best way to think about this is to think about this in the language of gauge theories. The covariance story here involves a topological gauge field and its associated field strength, and the gauge covariant topological charge, which is the right thing to work with, is no longer nilpotent because it's a gauge covariant derivative. It's not an ordinary derivative, but it anti-commutes to a lead derivation along a field strength. Okay? And the story I wrote down, roughly speaking, should hold for any temperature. However, the discussion I'm going to sort of invoke will only be true for high temperatures because the KMS condition which relates operators across the Euclidean time circle is non-local and discrete. So I actually don't know how to make this precise, although I can speculate if people are interested afterwards for arbitrary temperatures. In the high temperature limits, here is a heuristic that sort of underlies the technology that we are assuming. In equilibrium, we said you can think of the thermal circle being fibered over a spatial geometry. Imagine for a moment that the same picture holds out of equilibrium, at least when you have high temperatures and when things are slowly enough varying both in space and time. The heuristic is that you have a Lorentzian spacetime, and on top of the Lorentzian spacetime, you have a thermal circle fiber. Now, this basically says that time has become complex, with the imaginary direction being compact, but this is too much data. You've added one extra dimension. The way to get rid of it is like the way we get rid of in gauge theories, and that's what the KMS condition is instructing us to do. You ask that any slicing of this Lorentzian fibration leave you the same physical information. In other words, you gauge the symmetry of locally going around this thermal circle. That statement is a statement of thermal equivariance that I mentioned to you earlier, and that's basically given by this gauge algebra, where if you have two gauge parameters, you take one of them and you take the Lie derivative of the other along the thermal circle parameterized by this vector beta. So in this limit, in the high energy limit, I have high temperature limit, I have assumed that I can make this continuous. All I motivated for you before was for the discrete case. Yes. So, but I'm only going to work with a continuous thing because this is what I know how to work with. Okay. So, as I said, I can speculate what happens in the discrete case, but there are technical things that I don't know how to make it work. Now, the surprise for us is that this construction exactly reproduced this empirically observed symmetry that we have cooked up in the context of our attempt to classify hydrodynamic constitutive relations. Okay, so I'll now make contact with some other work that has been done in this context. I told you that thermal superalgebra was given by the three supercharges, two supercharges Q and Q bar, which didn't quite anti-commute to 0 because they were gauge covariant. They anti-commuted up to field strengths. Now, this gauge structure, once you've introduced the BRST symmetry, you also have a conserved ghost number. And this gauge algebra has exactly one object, which is covariant and has ghost number 0. Now, I'll make an assumption, which we made for independent reasons, which I can tell you later. I'll assume that the topological dynamics of the gauge field is consistent with the existence of vacuum where this ghost number 0 field strength takes the following expectation value. A constant expectation value, which I set to be -I because I've chosen some anti-Hermitian connections. And this basically ensures the CPT is spontaneously broken, that you have chosen a forward arrow of time in the theory. If you choose the sign opposite, that reverses time orientation. So in other words, this choice is what breaks time reversal symmetry in the problem. If you make this choice, if you just look at my algebra up above, it reduces to two nilpotent charges that anti-commute to a thermal translation. Now, this algebra at the bottom is something that people in the StatMech community have known about for a very long time, and this is exactly the algebra in the high temperature limit that our friends from MIT wrote down. So I just wrote down the folks from MIT, their algebra out here. They don't have the supercharges anti-commuting to a time translation, but they have it sitting inside a Bose-Einstein factor. Okay, a statistical factor that comes from the fact that the thermal period, the quantum, basically there should be an H bar here, which in the classical limit or high temperature limit linearizes to give you this operator. Okay. So now I can tell you a little bit about hydrodynamics itself. So why is this structure relevant to hydrodynamics? See, the response functions that one monitors in hydrodynamics are the following. You take the Schwinger-Keldysh contour and you turn on sources, but you turn on the same sources for a long time. And then, once you've done that, you finally go to the system and measure one average operator. Okay? So I've indicated this by saying that this color is different from this color, just saying that out here, you don't turn on the same source, you turn on slightly different, you asymmetrize the problem, so it actually gets some response. So the Schwinger-Keldysh correlators which are relevant in hydrodynamics are all differences but one average, something like an MHV correlator for those of you who know something about amplitudes. And because this is a slight deformation of the topological theory, because had this average operator out front not been there, the answer would have been 0. We should write down a topological field theory and then slowly deform it to get hydrodynamic response functions. But now the other useful fact is the following. Hydrodynamics has to emerge as a universal theory independent of what your microscopic variables were. Because it's true for n equals 4 super Young-Mills, it's true for a scalar phi to the 4th theory, and it's true for QCD. So it can't know, the low energy variables have to be suitably universal. They can't depend on what your microscopic structure was. And that's indeed true, and I'll just say it in pictures. So if you have a physical fluid living on some space with some metric, and here's our temperature and velocity fields, the variables of hydrodynamics are just how this physical temperature, this thermal vector, is obtained from some reference inertial configuration. Think of this vector beta I as just the vector 1, 0, 0, 0, and its push forward into the physical space is the dynamical data of hydrodynamics. For those of you who like deep brains, here's a world volume, and the world volume has a fixed reference vector field, and the push forward of that reference vector field in space-time is a physical velocity. So the non-trivial fact in our picture is that we also have this gauge field sitting there. Now with this data, it's very easy to write down hydrodynamic effective actions. It's basically an action involving the pullback of the space-time metric, this reference vector field, and objects built out of this universal gauge multiplier. There's an identity, because there's a gauge symmetry, there's an identity, which is the identity I wrote down earlier. It's simply the identity that tells me that the covariant derivation of the superfree energy current, which is defined to be the variation of Lagrangian with respect to the gauge potential, is equal to the total free energy contracted with the pullback metric Lie derived. And this is what leads to the picture of entropy inflow, because this equation written in superspace distills down to an equation in ordinary space as the ordinary entropy production term being given by the contribution from superspace. Let me end by contrasting this. So I'll just flash these examples. These are explicit examples for low order terms in the hydrodynamic effective action. But let me end by contrasting this with what we usually say in the context of 't Hooft anomalies. If you have a theory with 't Hooft anomaly, the way to write down an effective action is to couple it to a topological theory in one higher dimension and write down an action which is covariant, including the higher dimensional theory. And in fact, ADS-CFT really likes that, because that's how the actions for anomalous fluid dynamics emerged as suitable transgression forms from horizon to boundary. This picture of entropy inflow is something similar, except that now the inflow is coming from superspace. It's not coming from physical space. You're not adding one physical extra dimension of a topological field in the one physical extra dimension. You're adding a topological field theory in one extra, with two extra Grassmann directions. So with that, let me flash this slide about open questions and stop since I'm out of time.